Hello, everyone. Good evening.
Hello.
Good afternoon. Thank you for joining today's session. This will be our second for the data science track. So the topic we have today will be dealing on neural network regression problem. Okay, without wasting much of our time, let me just start sharing my screen in a moment. Okay, I believe everyone can see my screen now. Please, if you can, just let me know. Put it in the chat or just comment so I proceed. I hope everyone can hear me clearly. Okay, good. All right, so like I said, neural network regression with TensorFlow. So let me just, as usual, start with some theoretical aspects. So by now you should know a neural network is a series of algorithms that endeavors to recognize underlying relationship in a set of data through a process that mimics the way the human brain operates. That's basically neural network. So in this sense, neural networks refers to systems of neurons or artificial in nature. So there are many definitions for a regression problem because in neural network, you can have a regression problem or classification problem and what's not. So, but in our case, we are going to simplify it to be predicting a number that's a regression problem. So, for example, we might be predicting the selling price of houses, giving the information about them, or you are predicting the coordinates of a bounding box of an item, or you are predicting the cost of medical insurance for an individual. So moving on, that's just a little preamble. I'm talking about typical architecture of a regression problem. So there are many different ways to write neural networks. So, but this following outline I'm going to draw up is a generic setup for ingesting a collection of numbers, start finding patterns in them, and then acting some kind of target number. So let me reconnect my workspace. So this typical architecture, where we have the upper parameter and the typical value, we have the input layer shape. So this input layer shape is the same shape as the number of features that number of features you have in your data. Then the hidden layer is problem specific, a minimum number of one, a maximum unlimited. So this architecture I'm going to give you, it's already in the documentation for TensorFlow neural network. You can actually go back to documentation, you see how it's done. I got to explain what I'm explaining. So then there's a parameter we call neuron per hidden layer. Then there's the output layer shape. Then there's the hidden activation, usually ReLU, known as the rectified linear units. Then there's the output activation. It can be non-ReLU, logistics, or TAN. Then there's the loss function, just like the normal metrics in normal machine learning, the mean squared error or the mean absolute error. Can combine both. Then there's the optimizer, known as either SG. I already have their own documentation. You can go back and check on it. I'm not going to do much on that. So this architecture was gotten from the source was adapted from hands-on machine learning with scikit-learn, Keras, and TensorFlow. It's a book by Aurélien Geron. You can search on it for more. Okay, let's get down into the code. As usual, I will import my TensorFlow flow. I check the version I already have installed on my notebook. So I have version 2.1, 2.0. So at first, before we work with real life data, I'm going to be explaining how neural network work with creating a dummy data. So since what we'll be doing today is a regression problem, I'm going to create a linear data, that's a straight line model. So using my numpy matplotlib, so I'm creating the X and the Y label, creating a linear data number of numpy array. So this is a straight line, this is a regression problem. I'll just start on the main basics. So this is a straight line regression model of data. First of all, that's our data. So explaining regression input shapes and output shapes, one of the most important concepts when working with neural networks are the inputs and your output shapes. The input shape is the shape of your data that goes into the model. The output shape is the shape of the data that you want to come out of the model. So this will differ depending on the problem you are working on. So this pictural view explain more. Just like saying, for example, want to impute data will be this particular shape, a shape of 3 that probably are checking the amount of the bedroom, the amount of the bathroom or the garage shape or whatever it should be represented in numpy arrays or tensors. That will be your input. Then passing it to your machine learning algorithm, the output will be a single shape. That is the amount. So what this image is doing is just explaining the input shape, giving you the output shape in neural network. So let's move on to steps in modeling with TensorFlow. Before I gave the architecture of it, but now these are the steps in modeling with TensorFlow. First off, you create your model, compile the model, and fit the model. When creating the model, this means by piecing together the layers of neural network yourself, either using what we call the functional or the sequential API. It's in the TensorFlow documentation. Or you can import a previously built model, known as, this is often known as transfer learning. So there are previously built model, you can import it and fine-tune it. So instead of going through the process of creating your own neural network yourself, some models are already pre-trained, just import and fine-tune it. Then you can compile a model. This defines how a model's performance should be measured, as well as defining how it should improve as the optimizer. And lastly, fit the model by letting the model try to find patterns in the data. So we'll be working with, since I'll be building the model from scratch, we're working with the Keras sequential API to build a model for regression data. I won't be explaining much of the Keras sequential API. You still have to go back and check the documentation. So, but I'll show you the structure of how it is done. So first off, creating a basic neural network model. First, I will set my random seed to 42. This function is this way of building my neural network in the Keras sequential API documentation. There's functional, there's sequential API. So I'm following the sequential API documentation. First of all, you pass your model using the Keras. That's TensorFlow.keras.sequential. Then inside it, you have your layers. So here, I'll be creating a simple model with one layer. Then next to compile the model, I'll compile the model, set the loss function to mean absolute error. That'll be my loss function. So then the optimizer, I'll be using the HGD optimizer. That's stochastic gradient descent. Then my metric is the mean absolute error. And after which I'm going to fit the model. I'm running for 5 epochs. What epoch means is how long you train the model. So remember we created the dummy data, a simple linear regression data previously. So that's what I'll be training into this model. So running this particular code, see the epoch, the mean absolute error was loss function of 16, mean absolute error of 16. So let's check out our F and Y, then we'll make predictions. This is a data set we already created previously. I could guess if I want to predict my S data, since this is 14, in my data, the Y data was 24. I could predict the number of 17. The answer should be, let's say 27. So let's predict at 17 to see what to get. So our model is terribly bad predicting -12. It doesn't really go well at all. So it's not even close to 27. So other steps to do will be to improve the model. The way why we should improve your model is let me go back. I think I wrote that here. Okay. Another way of improving your model is by you alter every step of how you created your model. First of all, when you created the model, you might want to add more layers. My first model I did was just one single layer. You can, after compiling the model, you can increase add a learning rate function, or also train it for more approach. So I have a picture video to explain how you improve a neural network model. So improving the model, first of all, you can add layers, which is this box here. You can see my cursor very well. Adding layers. You notice my first model was just a single layer, the particular line here. Then you can increase the number of hidden units, which is this column. Number of hidden units. In my model, it was 1. I could decrease it to 100 and have the next one 100, 100. Then change the activation function. The activation function, which we had before, I didn't include it, so we could put ReLU. Then you can change the learning rate by putting the standard learning rate you can use. Browse more about that, you would have an idea of that. That is 0.00 beta. And also you can train for longer, which is the approach. So there are different ways for you to improve your model. Just need to know which step to apply. So going back to our model, I would create the same model as above, compile the same model as above, but this time we'll train for longer, train for 100 approach. Last time train for just 10 or 5. So running this code, okay. Then let's run X and Y again. So model of predict. See, this time around, it's predicting 30. The right answer should be 27, but it's still not bad. So because we improved the model is performing a little bit better. So this is just like a simple way of explaining how you can improve your neural network model. The previous time, what we had was the neural network error was -12 or so. So after we improved the model, had a value of 30, which is close to 27. So after that, it's just like the normal step with your normal machine learning method. So you can also evaluate your model. Normally in neural network, the typical workflow you can do is you're building a model, you evaluate it. You build the model again by tweaking different parameters, you evaluate it. You build again, you tweak, you evaluate it. You have suitable value you're looking for. So this time around, we're using another bigger data set before we work with a real life data. We'll still explain something more. So this time around, I'm creating a dummy data from the range of 100 -100 to 100 space of 4. That's our S data, and my Y data, and my NumPy arrays. And checking the length of our samples, it should be 50. Okay. So this time around, I'm going to put it in an S train and Y train. That's 80% and 20%. test data. After that, I'm going to be plotting the data to see our training and test data. So these are training and test data. What this image is showing 80% train, 20% tested data. That's what this image is implying. With this image, if I make predictions, I would see how my predictions are performing. So let me just show you there. So creating a model this time around, I'll put an input shape just like the same model as we did before. Previous model, compiling it same as before using HGT. This time I'm not using the Adam optimizer. Then I would train for 100 inputs. Then the meaning of these variables here is so that you won't be seen as the model is training. Those numbers that are displayed should not display. So that's the essence of this variables here. After that, you can also do what we call model.summary to tell you, to show you different variables in your model, to show you the layer, the amount of layer, the aspect shape, the parameters, the trainable parameters, and all. So this is what this model.summary does. They're making predictions. Please, if I'm too fast, just signify by dropping in the chat. Of course, I'll go back and explain. You can drop your questions there. So viewing the predictions that this model, the predictions the model makes. So let me put it in a visual. So you understand better. That's what this code is doing. I created a function. I'm not going to explain much of how I do the visualization. So let's see how the model was performing. So if you notice this model is not really performing well. So this is our normal data. This is the predictions that are pretty much far away from the true label. So that's when you can now get to evaluate your model. So evaluating your predictions by using mean absolute error or mean squared error, we already know this by now. So the lower value you have for the mean absolute error or mean squared error, the better. So to evaluate it, that's the default one in your model. For example, in my metric, in my model, I put mean absolute error. So to evaluate it, I could just run a function called model.evaluate to return the loss function of the model as well as the metrics I already set up during compiling the model. So let's just do that model.evaluate. Showing a mean absolute error of 30. Alternatively, you can still calculate the mean absolute error using TensorFlow as tf.metrics.mean absolute error as your y-test and y-preds. And also the same for mean squared error if you don't want to use mean model.evaluate. All right, let me just create, I might need this later. I'll just create a function for the mean and mean absolute error. I'm using it later on. So we already ran some analysis with a small data set. So let's work with a larger data set like a real life problem. So this time I'll be using the medical cost data sets. We worked on this data before. It's an insurance data set. So it's from Cargo, but already hosted it on GitHub. So I'm going to import my normal libraries, then import the data. So these are the variables in my data. That's the columns, my data sets, the age, the sex, the BMI, the children, smoker, and all. So of course, we're going to process this data. Since we already have categorical columns, so I have to convert it to numerical column. So I'm going to use pd.getDummies to do this. Then put my X and Y. So my target column will be the charges that they're predicting the charges. The company will charge their customer. That's the insurance charges they'll pay for the customer due to the this other data. So that's the target column. Let's view the head features. So, okay, now normally to split your data into train test and S train and Y train, S test and Y test, using a test size of 20% and random state as 42. So we already know this part. So just okay. Yeah, sorry about that. I had a little break in transmission. Let me just go back to sharing my screen. All right. I believe everyone can see my screen now. So let me just continue. So run my S train and test train. So moving on, so creating a new neural network model now. Creating the same model as my previous model 2 that I created before. So I'm adding 2 new layers. That this is the first layer, this is the second layer. Then compiling the model using the same HGD optimizer, the my metric is mean absolute error, but I'm training for 100 approach. This is my new large data set. So let's wait for that to run. Take a few minutes. All right, so that has trained. Let's evaluate the model. So we see we have a mean absolute error of 8,716. That's a bit high. So our model didn't perform very well. So let's try a bigger model. Like I said before, you can increase the number of layers or change the units, number of units in each layer, and also change the optimizer. So I can see there's a question. Mind you, this session is a coding session. It's not the compulsory technical webinar. There's no password or attendance repass. So just focus on the session at hand. So moving on, let's train another model that to improve the model. So this time around, we added what I did there. I add an extra layer and increase the number of units. Previously, the first one we had was 2 layers with just 1 unit. But now I have 3 layers with units of 100, 10, and 1. So this is important for the output layer. So this time around, I changed the optimizer. Previously, it was HGD optimizer. Now I'm using the Adam optimizer. Yeah. Then the same metrics mean absolute error. So I'm going to run and compile and fit this model, training for 100 epochs. Okay, then moving on to evaluate the model, let's see if this will be better. Yeah, this was quite better. The previous one, we had a mean absolute error of 8716, but now it's 4770. So it's improved. We can still improve this model more by increasing either the number of layers, number of units, putting what we call a learning rate of 0.0001, then training for more inputs, like I train more for like 200 or 300 inputs. So these are ways you can tweak your model to have and evaluate it to see if you have a good model. Since you're using depending on the metrics you're using, as I'm using mean absolute error, the less value, the better. So let's put this in a visual to see the loss function. So if you notice what this loss curve is doing, is showing how the model training, so it's actually reducing as the number of epochs is increasing. So meaning that's my mean absolute error. So the loss and the mean, they just intersect each other. That's they are together. That's why you are not seeing this loss. The loss is the blue color, and the mean absolute error is this yellow color, or whatever this color is. Okay, so from this, it looks like our model performance will decrease as we train for more epochs. So hence, you can try to train further with more epochs. You can train for 200 or 300 epochs. So what this tells us is that you cannot be asking, so how long should you train for? It depends. So it actually depends on the problem you are working on. Sometimes training won't take very long. Other times it take longer for you to train. Sometimes training a neural network model, you can be training for like 2 days straight. So it depends on how large your data set is and what you're trying to, that's the problem you're trying to solve. So a common method is to set your model training for a very long time. For example, you can train, I just train for like 100 epochs. I can train for 1,000 or 3,000 epochs. But what you can do is to set what we call early stopping callback. So what this early stopping callback does is that it will stop the model if it notices that there's no improvement in your training. So for example, I set it to like 2,000 epochs. That goes to 1,500 and training 1,600, 1,700. There's no improvement. The early stopping callback function would stop training and provide the value for that. So instead of training longer and you know that the model is not improving, this early stopping callback would automatically stop when the model does not improve. So doing this, let's try and train for more epoch to see if our model would improve. Okay, then let's evaluate the model trained for 200. So you see that there's slight difference. The previous mean absolute error we had was 4,700. After training for more approach, 3,496. So with this, I can try to train for more approach or improve my model, increase the learning, the input layer, the numbers, add the learning rate, train for more approach, add more data. So there are ways you tweak your neural network model. So now let me just plot the loss curve to see. So you can see that as the input also, as we trained longer, the model was performing better. So that's what this loss function is. So there's something that's called by preprocessing your data, you can also preprocess your data to improve your model, even after increasing the input layer, the in layers, and all that. So a common practice, we already know this by now, there's normalization and standardization. So this normalization process is killing all values from the original range. For example, e.g., between 0 and 100,000 to between 0 and 1. That's what normalization does. Then there's standardization, which converts all your data to unit variance and zero mean. So this is done by subtracting the mean value from the target feature and then dividing it by standard deviation. So all these are just talk, there are codes for that that will just run for you. So bringing back my data that wasn't processed. So this is it. So using our normal cyclic length, we can preprocess the data. We can use the make column transformer to build a multi-step data preprocessing function. We can use the min-max scaler to make sure all numerical columns are normalized between 0 and 1. Then we can use one hot encoder to encode the categorical data into numerical data. So let's pass this in this code. Let me explain what this code is doing here. So I imported my make column transformer, the min-max scaler, and one hot encoder of scikit-learn. Then putting this in a dictionary. So that's the make column transformer. I'm putting the min-max scaler. I'm going to scale the numerical column and make everything be in a value between 0 and 1. Then I'm going to one hot encode the categorical columns. That's what this code is doing here. And as usual, I put my S and Y data. Target column is the charges. Drop that from S. Then build our train and test split. Then fit the model. Then transform the training and test data with normalization. That's the min-max scaler. That's from what we have here. So this make column transformer is like a pipeline. That's what it is. You can go back and check documentation to know what it does. It's from scikit-learn.compose. So it's like a pipeline that can pass your in your preprocessing codes. So I pass in my min-max scaler and one hot encoder. So just did that the transform S3 and the S test. So now let's run this code. Then let's no need to view that. So to see our shape. Okay, now building our model. So I'm going to be using the same model as before. That's my model 2 bit before with the Adam and 200 inputs. So running that. So we'll see a difference of our previous model with that in a data that wasn't really preprocessed, that was all normalized, and with this our data set that was normalized. So we can see a difference if the model improved or not, the mean absolute error. So that is done. So let's evaluate our model. So if you notice, it improved. It was before 3,900, now it's 3,167, mean absolute error and loss. So let's compare both models. So these are the difference. So even after tweaking my neural network model, instead of tweaking it more, I process my data, normalize my data using min-max scaler. Then after this, I can further tweak my model on this my preprocessed data by training for more approach, by increasing the hidden layers, by putting a learning rate. So many other things I can do to improve the model. So this is just like a basic run through of how you create a neural network model. Mine is a neural network regression problem. So it's basically the same thing for a classification problem. Just that you have how you process your data for classification problem and all that. So basically that's what we have for today, just to show you a brief intro on how neural network, a simple way of showing how neural network is being built, how you compile it and process your data. So if you have any question, please just drop it in the chat box. I'll be happy to give a reply. If there's any part you don't understand, from the input layer to the optimizers to how this model was set up. So mind you, I was using a Kira sequential API. There's another one called the functional API. So this is when you're building your model from scratch. So there are other, you can also import, like I said, import previously built model known as transfer learning, and then fine tune it to what you want. So basically that's it. We have a few minutes for questions. If you have any questions, this part you don't understand, can you drop it in the chat box? Let me stop sharing. Any question? Okay. So I guess everybody had it was pretty much understandable. Okay, that's good. Lovely. All right, to give a brief through of what is expected for you in your tag along projects. I don't know if you've gone through it yet. There are two parts to do your quiz, and the second part is the project you have to do on Cargo. You can work on it on Cargo or download to Collab or your local machine. But what you need to do is, second part, handle the project. What is needed for you to submit is it's like a competition that has already passed, but you can make your submission, that late submissions. After that, since the competition has already passed, they will not automatically take you to the position where your submission will be. So, but they will give you a result that is based on the metrics that you need to submit. Just screenshot where your result would have placed you in. Screenshot that and also your score. Then you submit alongside your repository showing what you did with the code and all that. So I guess that's pretty much understandable. So once again, thank you everybody for joining today's session.